last time. Right, we did the fundamental theorem of calculus. Okay, so the fundamental theorem of calculus. This is the fundamental theorem of calculus. Has two parts. Part one is every function has an antiderivative, every continuous function, if f is continuous on a to b and x is between a and b, then if we make a function called capital F by integrating from a to x, f of t dt, this will be an antiderivative, is an antiderivative of f. Why? In other words, if you take the derivative of this, take the derivative of the integral function up to x, you get exactly the value of f at the point x. Okay, so again, here's a to b, here's our little f, here's some point x. The rate of change of accumulation of area at that instant is the height of that instant. Okay, fundamental theorem of calculus, part one. Most of these functions, so i.e. all continuous functions, f, have antiderivatives. In other words, this is an antiderivative. Most of the time, you can't write them down. Most capital F can't be expressed. This is a fact. I'm not proving this fact. I'm just telling you this fact. It can be proved. Most capital F can't be expressed using elementary functions, using powers, as polynomials, using polynomials, trig, exponentials, logs, etc., and concatenation of these things. Okay, so almost none of the time, if you give me some random little f made up of polynomials, trigs, exponentials, logs, we know we can differentiate any of those things. We have the quotient rule, we have the product rule, we have a chain rule. Almost none of the time can we write this capital F, this antiderivative, using those things. But if we know an antiderivative, if we happen to know an antiderivative capital F, i.e. f prime of x is equal to f of x, then we can indeed evaluate the integral from a to b of little f dx just by sticking in the value of f at b minus the value of f at a. Okay, this is what we covered last time. The fact that it's an antiderivative means the fact that the integral from a to x is an antiderivative means that if we know any other antiderivative, the two differ by a constant, and when you subtract it, forget about the constants. The constants cancel out. My preferred way of writing this is to say that if you integrate the derivative of a function over an interval, it's the same as the integral over the boundary of the interval of the function. Okay, where boundary, if I have an interval a to b, if I is the interval a to b, then I'm thinking of the boundary of I as the evaluation at b minus, because I has an orientation, there's an orientation to this, there's a positive contribution from this endpoint in the direction of the orientation, there's a negative contribution from the other endpoint. This looks kind of funny. Okay, I'm only writing it this way so that when you get to Calc 2 and 3 and 17, and you learn Stokes' theorem, you're going to learn something called Stokes' theorem, and you learn something called Green's theorem, and then you're going to take calculus on manifolds, and you'll learn de Rham cohomology. It's all this. The fundamental theorem of calculus is a duality. This is a duality. I'm just planting seeds for the future. You don't have to understand these words. Just let them go in there and start to coalesce. It's a duality between the boundary of a function, and boundary of the space on which the function acts. Boundary of space. ... A discussion to be continued in future. Future you will look back at this and go, oh, wow, that's what we were doing when we were doing Green's theorem and we were doing de Rham cohomology on manifolds, whatever else you did. Okay. Okay. Just plant that seed. I realize those words don't mean a lot to you right now. They might mean even less since you can't read them. Boundary of the function and boundary of the space on which the function acts. There's some kind of duality. That's what the fundamental theorem of calculus is really representing. There's a very profound idea, one that will continue again and again, continue to haunt you in your dreams or nightmares again and again. Okay, so integration, once we know this fundamental theorem of calculus, integration boils down to, or the next little bit of integration techniques. So integration, our integration skill, our integration techniques come down to finding antiderivatives, recognizing antiderivatives, patterns for finding antiderivatives. How do we find such things? Let's do one example that I think is kind of fun. Maybe you'll like this. What's the integral from 0 to 1 of x times the square root of x times the cube root of x times the 4th root of x times the 5th root of x, and so on forever? This is something that might blow your mind, but in fact, it's something we can very easily evaluate already using the techniques that we have. So this is an integral. I have an x to the 1 times a root x. That 3 is for the cube root. It's not an x cubed. This looks like an x to the 4. It's an x and then a 4th root and then a 5th root and a 6th root and so on. So this x is to what power? 1/2, x to the 1/2 times this x is to the 1/3 to the 1/2 to the 6th, right? So that's over 1 over 2 times 3. This x is to the 1/4 to the 1/3 to the 1/2. 2 times 3 times 4. And the next x will be to the 1/5, 1/4, 1/3, 1/2. 2 times 3 times 4 times 5, and so on forever. Do you remember the definition of e to the x? We discussed this. 1 plus x squared over 2 factorial plus x cubed over 3 factorial. 2 factorial is 2 plus x to the 4th over 4 factorial, and so on. And this is why when you differentiate e to the x, here you get 0, here you get 1, here you get a 2 comes down, kills off that 2, leaves an x. 3x squared over 3 factorial is an x squared over 2 factorial, and so on. You remember we had this discussion? And this is why the derivative of e to the x is e to the x itself. And so what about the number e itself? E, which is e to the 1, you remember this, is 1 plus 1 plus 1/2 plus 1 over 3 factorial plus 1 over 4 factorial plus 1 over 5 factorial, and so on forever. You remember that? So what is this? What's the power of x here? I have x to the 1 plus 1/2 plus a 6 plus 1/24. It's almost e. E has an extra 1 at the start. E minus 1. It's x to the e minus 1 dx. This problem is too hard. This is not the kind of thing that I would ask you on the final, but we know the power rule. We know the power rule. Here's the point. We know the power rule for derivatives. The power rule for derivatives says that if I want to differentiate x to any power, that's easy. It's just alpha times x to the minus 1. Every integral, every derivative rule has a corresponding integral rule. That means we have an integral rule, which is that the integral of x to the alpha, or rather the antiderivative of x to the alpha for any power alpha, is x to the alpha plus 1. But if I differentiated that, a factor of alpha plus 1 would come down, so I need to divide by alpha plus 1. Plus c. Okay? Any antiderivative will be this one plus a constant. So here we have alpha equal to e minus 1. So an antiderivative of e to the x to the e minus 1 is x to the e over e. and we'll evaluate plus c, but we don't need the plus c if we have a definite integral, if we're actually computing an area. So if we're computing this area, we evaluate as x goes from 0 to 1. When x equals 1, I get 1 to the e is 1 divided by e, minus when x is 0, 0 to the e, 0 to the e, not e to the 0, 0 to the e is 0. And so the answer is 1 over e. This crazy, crazy infinite nested integral is nothing but our old friend 1 over e. Okay. Cool, fun. Euler liked this kind of stuff. All right, let's get some more practice with other kinds of rules. So every time you have a derivative rule, let's write this down. Every derivative rule has a corresponding integral rule. Again, rule means shortcut. Shortcut. Okay, so what about our exponential rule? What's the derivative of a to the x? Yes, a to the x times ln of a. Beautiful. So what's the integral of a to the x? Indefinite integral. In other words, what's an antiderivative of a to the x? A to the x over ln x, ln a. Plus c, thank you. Okay, always plus c. If it's an integral, if it's this symbol means give me an antiderivative. Actually, it means give me all antiderivatives. This symbol means find the area. What's the difference between this symbol and this symbol? The limits, exactly. The limits of the integration. This has limits, so it's a definite integral. It's asking for an area. This does not have limits, which means it's just asking for an antiderivative. This is called a definite integral. Have we used this terminology before? This is a definite integral. Definite integral. That is area. This is an indefinite integral. There are no bounds, which means don't give me a number, give me the antiderivative. Or give me all antiderivatives. And they all differ by a constant. Okay, that's an exponent rule. We have the sine rule, you know, all of our trig integrals we know and love. Here's a very powerful thing. We have the chain rule. This is the thing we're going to spend most of today on. What's the chain rule? If I have a big function f of an inside function g, and I differentiate this, what is it? Exactly, f prime at g of x times g prime of x. This has a corresponding rule in integral calculus. Does anybody know what the corresponding rule is called? U-sub. Okay, the opposite of the chain rule is something called u-substitution. So let's see this in action. U-substitution. Let's do an example. Here's an example. Here's a nice example. Okay, I want to know the antiderivative, indefinite integral, of x cubed plus x to the 21st power times 3x squared plus 1 dx. It's just a polynomial. All we have to do is multiply this whole thing out. Exactly. We do, yeah, Jenny? Yes, we do not want to multiply this whole thing out. This will be an awful, god-awful mess if we try to multiply out the 21st power of x cubed plus x times this other thing. But Jenny noticed something. Jenny noticed, so notice, this is where the pattern recognition, okay? This is the pattern recognition component of calculus. You need to be able to spot patterns. How do you get good at spotting patterns? Practice, 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 okay? So what Jenny is noticing is that if u is equal to this inside thing, x cubed plus x, then du meaning in the sense of differentials. Remember, we spent all this time talking about differentials. So u is a function of x. When x changes, how does u change? So if I just take the differential, What's this? The differential of x cubed, 3x squared dx. And what's the differential of x? 1 times dx. So the dx actually we can pull out of everything, and you'll get used to doing that immediately. So you just differentiate this, 3x squared plus 1 dx. I have a 3x squared plus 1 dx. That's the pattern. If you notice the pattern, that here was an x cubed plus x, and here is something that smells an awful lot like the derivative of this. That means I can interpret what's in here as this u. So I'm going to change variables from x's to u's. This is exactly u. This whole thing is exactly du. This whole thing is exactly du. And so the integral becomes u to the 21st power du. Everybody see that? Now I know the antiderivative of u to the 21st power. U to the 22nd power over 22 plus c, right? I want all antiderivatives, but the original, that doesn't tell me what the antiderivative, this is a function in x's. I need a function in x's. How do I go back from u's to x's? I just stuck it back in. Yeah, u was x to the, whatever it is, x cubed plus x. So this is x cubed plus x to the 22nd power over 22 plus c. That is the antiderivative of this god-awful complicated thing. So if you were to multiply, if you were to do this, x cubed plus x to the 21st power, multiply that all out, get this god-awful polynomial. It's going to have 40-some terms. You integrate all those terms, term by term, and you factor, you will find that you multiplied out x cubed plus x to the 22nd power and divided by 22. Okay, you see how much power this technique has? Let's do it a whole bunch more until we get good at it. Okay, how would we figure out something like the antiderivative of square root of 2x plus 1 dx? 2x plus 1, some nice function. What's its can we think of a function whose derivative is this? I don't know. For me, it's hard to just make a function like that up. What might we try as a u? Yes. How about making the inside of the square root a u? Maybe that'll make our lives easier, maybe not. So let's try u is 2x plus 1. Then what is du? 2 dx. 2 dx. Now I don't have a 2 dx. I have a dx. Yeah, so 1/2 exactly. That's just a constant. That doesn't bother me at all. 1/2 du is equal to dx. Now I have all the pieces. This is the integral of u to the 1/2, u to the 1/2 power, instead of dx, 1/2 du. 1/2, which I can pull all the way outside, 1/2 du. Everybody see that? Okay. Great. So I know how to integrate u to the 1/2. That's u to the 3/2 divided by 3/2. In other words, times 2/3. And let's not forget the factor of 1/2 that was already there. Plus c. Every time, plus c. And what was u? So the 2's on top and bottom cancel. I get a 1/3. What was u? 2x plus 1. So this is 2x plus 1 to the 3/2 plus c. What should you always, Nimmer, you got a question? Why did I divide by 2? So here I just have a dx. I don't have a 2 dx. So if I divide both sides by 2, then the dx is right there. And so I know that I'll need a 1/2 du. Does that make sense? Other questions? When you find an antiderivative in a problem like this, should you just say, okay, I got it. I'm sure I didn't make a mistake. You should, somebody said, take the derivative. Okay, check your work. Always check your work. We didn't do it here, by the way. Let's check our work here. If I take the derivative, then a 22 comes down. kills the 22 in the bottom. I get x cubed plus x to the 21. Chain rule times 2x squared plus 1. That's exactly how we found this. Okay, so check your work. Always check work. Always check by differentiating. Okay, the constant I never have to worry about. If I differentiate this, the 3/2 comes down, makes that one. Okay, let's do it. Let's differentiate this. d dx of this is, I get a 1/3. The 3/2 comes down. I get a 2x plus 1 to the 1/2. Chain rule, 2x plus 1, the derivative is 2. And the 3's cancel and the 2's cancel, and I get square root of x plus 1, which is exactly what the integrand was. Okay. Always check your work. Any questions? Bless you. Let's do another one. How about the integral of secant squared of 5x plus 1? What's the antiderivative of secant squared of 5x plus 1? How are we going to do this? Yeah, let's use so secant squared, we know an antiderivative of secant squared. Tan, the derivative of tan is secant squared, but there's this weird function inside. That's okay. If u is equal to 5x plus 1, then du is equal to 5 dx. So 1/5 du is equal to dx. Again, I just want to see every term exactly as it occurs. So this is equal to secant squared of u times 1/5 du, 1/5 du. The antiderivative of secant squared is tan u plus c. And so this is a 1/5 tan of 5x plus 1 plus c. Make sense? Pretty easy. So, sorry, say it again. Okay. Should we check? Let's check at least in our minds. If I differentiate this, the derivative of tan is secant squared of whatever's inside. The derivative of what's inside brings down a 5 that kills that 5. Bless you. Okay. Should we make this the quiz? Let's try a quiz. Okay. Antiderivative of e to the x cubed times x squared dx. Take a minute. Work this one out. You guys don't have paper? Oh, yeah. All right. See if you can figure this one out. Give me a thumbs up when you got it. A couple people got it already. Some people are still working. Take your time. What are you guys using for your u? X cubed. X cubed is a good choice. Okay, then what are you going to do with the x cubed if you use x squared? You mean e to the x, the u. Yeah. So you're going to make, okay. So we're going to try e is equal to e to the x.
No, I mean like u is equal to x squared.
U is equal to x squared. Okay, if u is equal to x squared, go on.
And then what I did was that I substituted it. So it'd be equal to e to the x times u. It's the power.
Okay, x times u.
And then x.
Sorry, say it again.
So like I just did it multiplied by u with that in front of you.
The whole thing multiplied by u. Okay, and then what about dx? See, what you don't want is you don't want x's and u's mixed together. Because now you have something much more complicated. U is a function of x and x is a function of u. The reason all of these work is that we've gotten rid of all of the x's. It's very good that you did this because it gave us the opportunity to discuss common things people do. If you don't get rid of the x's, then you have something that mixes u's and x's, and it hides the dependence of one on the other. Yeah. Thank you for that comment. Okay, so we can't have the x's floating around with the u's at the same time. So those of you that did x cubed, how many of you did x cubed? Or yeah, okay. X cubed is kind of a natural thing because the derivative of x cubed is roughly x squared, right? The derivative of x cubed is x squared except for this factor of 3. That's okay. That doesn't bother me. Now it looks like something that we recognize. So this is e to the u, and x squared dx is a third du. So that's a third du. And the antiderivative of e to the u is e to the u. So here's a 1/3 e to the u. Maybe I won't even bother putting the u there. I will put the plus c. U is x cubed. Okay, so give yourself a point for this, a point for this, a point for this, and a point for that. What is that? 4 points, something like that. And pass them over, please. And Peter, thanks. How many got 4 out of 4? Okay, pretty easy. Yeah, that's a really, really good point. It's a really good point. Let's put it here. For u substitution to work, for u sub to work, need to convert all x and dx's into u and du's. Okay, having them mixed together is going to cause problems. You could, I mean, if you tried it the other way, you could get something like e to the u times square root of u. If u is x squared, then you get this, and then over here you're sort of struggling to find dx in terms of u. You get something much worse than. Well, but it's e to the x. The exponent is x times u, so that's like e to the x to the u's power. So that's really bad. Makes things much more complicated. Okay, let's try a couple more. How about let's get a couple of trig integrals in here. Can we integrate tan? What is an antiderivative of tan? What is it? You've seen, you knew. Did we talk about the antiderivative of tan? No. Yeah, because we didn't have the tools yet to talk about how you would find such a thing. How could we find such a thing? Yeah, exactly. Tan is sine over cos. And the thing that's bothering me is it the numerator or the denominator? What's harder to integrate? The denominator, right? The denominator, the numerator is kind of like, is there, but the denominator is the thing that I'm worried about integrating. So what u substitution should I use? The denominator, yeah, u is cosine x. Let's try u is cosine x. What's du? Negative sine x dx. Excellent. I don't have the minus sign, but that's okay. I'll put the minus sign in, In other words, I'll just dividing both or multiplying both sides by -1. Sine x dx is du. Cos x is u. Hopefully this doesn't bother anybody. You're used to seeing things, you're used to seeing it like this, -1 over u times du, right? This is a height, this is a width, but it's just as well to write it like this, du over u, no problem. So far, so good. What is an antiderivative of 1 over u? Bless you. ln, so I get negative ln of u plus c and absolute value sign, because if it's a abstract, if it's an indefinite integral, in other words, just an abstract antiderivative, I don't know if u is positive, negative on either side. I have an antiderivative. To capture both of those, you put the absolute value. Okay, and that's it. We're done. It's natural log. Do not forget to return things to x's. If it's an indefinite integral, you want natural log is not the antiderivative of tan, but negative natural log of absolute value of cosine is an antiderivative of tan. And is there a better way to write this? If I put that minus sign into the exponent, in other words, this is ln of cosine x to the -1, it's ln of secant, exactly. Natural log of absolute value of secant x. The negative. The derivative du is negative sine x dx. So in other words, negative du is sine x dx. I have here sine x dx. I need that minus sign. Okay, does that make sense? Yeah. Oh, this -1. So I'm just saying, I'm just using the log rule that if I have a log of something to a power, that power can come down, or conversely, that power can come up into the exponent. Okay, so it's to the -1 power, in other words, 1 over cosine. If you left it here, perfectly fine. Perfectly fine to leave it here. Let's test if this formula makes sense. What's the derivative? D dx of ln absolute value of secant x. Oh boy, the plus c I don't care about, obviously. The derivative of ln of absolute value is 1 over secant x, chain rule, secant tan, plus c. No plus c for derivatives, only for integrals. The secant cancels out, and that's exactly the tan that I wanted to see be the integrand. Okay, so that's checking our work. Make sense? Oh, listen. Yes. So how did I get a du over u, and where did the sign go? The sine x dx is du, or negative du. So I got negative du, and then there's a cosine in the bottom, and cosine is u. Okay, and then this is really what I mean, but a shorthand for this is to write it like this. Okay, this sometimes confuses people. It's a natural notation, but it's confusing notation to some. Takes a little getting used to. You're right to be suspicious of it. Yeah. Okay, does this make sense? Ask me, there's 10 other people that are confused. Please. What were you looking at? The sine function. The sign on top, because now I've written too many things. The sine and the dx, let's do it like this. The sine and the dx together make du, or negative du. Does that make sense? Yeah. We set the denominator equal to u. Yeah. What you want to look for when you're doing a u substitution is, what do I know how to integrate? I know how to integrate e to the x. I do not know how to integrate e to the x cubed. I know how to integrate 1 over u. I do not know how to integrate 1 over cosine of u or something complicated like that. So look for a simple function and see if its derivative happens to be floating around. Does that make sense? Let's do a couple more examples. Okay, let's try this one. Example, the antiderivative of 2z over the cube root of z squared plus 1 dz. Just to mix up the variables a little bit. What do you have in mind? Make u equal to z squared plus 1. That's one option. That is certainly one option. Let's see what happens if we make u equal to z squared plus 1. I see why you would want to do that. Then you would just get a u to the minus 1/3. That's a reasonable thing to be able to integrate. Okay, then du will be 2z dz, 2z dz. I have a 2z dz very conveniently floating around. So this is an integral of u to the minus 1/3 times minus 1/3 times du. And the antiderivative of u to the minus 1/3 is u to the 2/3 divided by 2/3 times 3/2. Let's see. How many of you are going to get a point off on the final exam for forgetting a plus C? Thank you for your honesty. Okay, that's why I keep, please don't lose that point. Come on. Like, enough. Okay, so this is 3/2. U is z squared plus 1 to the 2/3 plus C. Or, did anyone try to do it any other way? You could have also tried taking the whole denominator to be u. What if we took the whole denominator to be u? Z squared plus 1 cube root. I agree. I would probably choose this. This is kind of more natural for me. But if you had tried to take the whole denominator for u, let's see what if we can work it out that way. Then du would be z squared plus 1 instead of to the 1/3 to the minus 2/3 with a factor of 1/3 coming down. Chain rule 2z dz. Do I actually have that floating around somewhere? Wait a second. If z squared plus 1 to the 1/3, this is z squared plus 1 to the 1/3. If that's u, then what is this? This is u to the minus 2, right? U to the minus 2. We don't want to mix the u's and the z's. Let's bring the u to the minus 2 to the other side. If I multiply both sides by u to the minus 2, I get u squared du. Let me multiply the 3 over here as well. 3u squared du is equal to 2z dz. Everybody see that? So then this integral, the integral 2z dz turns into 3u squared du, and z squared to the 1/3 becomes u. So this just becomes 3 times u. 3 times u. I know how to integrate 3 times u. 3u squared over 2 plus c. So this is 3/2. What was u? Z squared plus 1 to the 1/3 squared. So to the 2/3 plus c. 3/2 z squared plus 1 to the 2/3 plus c. Either way, it works out. Bye. Cancel the u's right here. Yes, absolutely. I'm canceling the u's on top and bottom, and I have 3u, and the antiderivative of 3u is 3u squared over 2. It's exactly what I'm doing. Yep. Yeah. Okay, does that make sense? So there are some choices in the u-substitution, there are some choices that work out, some choices that, sometimes there are multiple choices that will work out and give you the same answer. Sometimes there are multiple choices that will give you things that seem like they're different answers, but in fact, they're the same answer up to a constant. There's, do I have an explicit, I don't have an example of that on me. I should. I'm not going to come up with it off the top of my head. It's the weird logs and tans and stuff. Weird trig things can sometimes come with a weird inverse trig functions and logs have a tendency to do that. Let's do a couple more examples. Okay, here's a tricky one. Here's a very tricky one. What's the antiderivative of secant? Secant squared, I know the antiderivative. Secant by itself, does that have a nice antiderivative? Secant is 1 over cosine, but I don't have I need a sine function in the numerator to balance the cosine if I want to use sub. I don't expect you guys to be able to come up with this. Here's a very sneaky thing you can do. You take your secant x dx and you multiply the top and the bottom by what? Sine is a good guess, but sine would be a problematic. I already have a 1 over cosine. If I multiply by sine on top, I have to multiply by sine on bottom. And then sine times cos, you can try something like that. You can try something like that. In fact, sine times cos is another sine whose derivative is cos, but I have a sine now. So it's not, I'm going around in circles. Here's a very sneaky thing that somehow people figured out, that you can multiply top and bottom by secant plus tan. I'll show you in a second why you would think that that might have some benefit. Multiply top and bottom by secant plus tan. Let's just see what this is. Here I have a secant squared. Here I have a when I multiply this out. Let me put parentheses here, because many of you would put this on one side and not put parentheses. I'm still seeing floating parentheses, so let me just make sure I put them there, even though I don't actually need them because it's a separate fraction, separate from this thing. But okay, I have a secant squared x plus secant tan x all over secant x plus tan x. What do you notice? What's the derivative of tan? Secant squared. What's the derivative of secant? Secant tan. How crazy is that? So let's u sub the denominator. Exactly. U sub is secant x plus tan x. If that's u, then du is derivative of secant tan, derivative of tan, secant squared, dx. Okay, so the numerator just happens to be, this numerator times dx just happens to be the thing that we need for du. So this is an integral of du times 1 over u, which is ln, absolute value, thank you, plus c, thank you, and u was secant plus tan. So this is the kind of stuff that takes a little bit of doing to get good practice with. Same. Why is the natural log? Yeah. Okay, so let's go over that. If I look at the function 1 over x on the positive numbers, you're perfectly happy with why the integral, the antiderivative of 1 over x is ln x. Okay. If I look at the function negative 1 over x on when x is negative. This is when x is positive, on x being positive. When x is positive, in over here, 1 over x has a nice antiderivative. That's the natural log function. When x is negative, let's look at the function ln of absolute value of x. Ln of absolute value of x, when x is negative, if x is negative, then its absolute value is positive. So in order to make it positive, I have to multiply by a minus sign. So if x is negative, this is the natural log of negative x, which makes perfect sense. Natural log is only defined on positive numbers, right? So now let's differentiate this. So d dx of natural log of negative x. Okay, chain rule. Zane, take us through it. Yeah, so just 1 over x and then chain rule. -1. So isn't that 1 over x? So on the negative numbers, what's 1 over x on the negative numbers? It's like this. On the negative numbers, we also have an antiderivative to 1 over x. That antiderivative is ln of negative x. On the positive numbers, the antiderivative of 1 over x is ln of x. On the negative numbers, the antiderivative of 1 over x is ln of negative x. So we can capture both of those, whether x is positive or negative, in one fell swoop. Okay, so if it's an indefinite integral, then you want the absolute values. If it's a definite integral, it had better be a definite integral from 1 to 2. And then you want ln of the positive values, or from -2 to -1. And then you want ln of the negative of what's inside. Does that make sense? Thank you for asking that. I'm sure that we've gone over it several times, and I'm sure there's still people who needed one more refresher, and I'm sure there are people who will need one more refresher after. So keep asking, ask. Ron. If I had the integral of ln x from 0 to 1, okay. So 0 to 1, ln of x dx. You mean, do you need the absolute value or not? Or just what's the answer? Okay, the ln function, let's think about the ln function. Here's the natural log function, ln x. Here's the integral that you're asking for from 0 to 1. It turns out that this area is very negative. In fact, do we know the antiderivative of the natural log function? It has an antiderivative. It's another one of these sneaky ones. You guys happen to know what it is? Yeah, let's try x log x. What's the derivative of x log x? We need a product rule. Let me leave a little bit of room here. The derivative of x log x, we need the product rule. Let's say the first thing times the derivative of the second thing, plus the derivative of the first thing times the second thing. That's good. I almost get ln x. I get ln of x plus 1. How do I get rid of this plus 1? Yeah, I want to be able to minus 1 off of this, which means I should subtract x. So x log x minus x is an antiderivative of ln x. And so once you know that, you can say, okay, that means I know then an antiderivative, x log x minus x. If I evaluate this from 0 to 1, at 1, I just get 0 minus 1. At 0, I'm asking about x times ln of x. So which is it? Okay, let's compute this. Let's finish this calculation. Is this a finite negative area or not? That's the question. Okay, so when x is equal to 1, I get 1 times natural log of 1, which is 0, minus 1, minus the value, the limit as x goes to 0. So let's write this as the limit as x goes to 0 of x times ln of x minus x. X we know, x goes to 0. Okay, so the question becomes, what happens to this? How can you? Well, it's 0 times negative infinity. How could we try to evaluate this? L'Hopital. Okay, so we have one more thing to work out. This is a sort of aside, although it's a great question. Maybe we should put this on the final. What is the limit as x goes to 0 of natural log of x times x? I want to make it a fraction. Natural log of x over 1 over x So now let's try L'Hopital. Derivative of log x, limit as x goes to 0. Derivative of log x is 1 over x. Derivative of 1 over x is negative 1 over x squared. And so what is this? 1 over x times divided by 1 over x squared is 1 over x. There's a negative sign, so it's a limit as x goes to 0. Negative 1 over x times the reciprocal of this, x squared, over 1. So this is x. When x goes to 0, negative x as x goes to 0 is still 0. So this thing goes to 0, and I have a 1 times natural log of 1. This is 0 minus 1. So this whole area under the log function is negative 1. Sorry? Minus 0. Yes, but minus 0 is the same thing as 0. Here, this is the value of when x is equal to 1. So I have 1 times log of 1 minus 1. 1 times log of 1 minus 1. But this log of 1 is 0. So this is just 0 minus 1. This is the only thing that survives. Here we have to take a limit. Yeah, this one's too complicated for the final. But anyway, is this what you're asking? Yeah. So the question was, is this area finite or infinite? It turns out it's finite. And it turns out it's 1. Okay, it is what it is. All right, we got a lot to cover. Some more tricks. More calculus tricks. How about the integral of sine? What's the antiderivative of sine squared dx? I don't have a cosine. If I had sine squared cosine x, I'd be in business because I could do a u substitution. What am I going to do with this thing? If we make u sine, then I have u squared, but I'm missing du. I don't have a cosine to match that sign. Say it, Ron. Yeah, but does that have a nice antiderivative? Ying, you had something for us? Let's remember. I think maybe I'm mishearing you or interpreting what you're saying. Remember your double angle formulas? What's cosine of 2x? Sorry, Nimmer. We need them all. I told you we needed them. What is it? It's cosine squared minus sine squared. Does that ring a bell? Cosine of a plus b is cosine of a cosine of b minus sine of a sine of b. So if a and b are equal, you have this. No, Peter, come on. We saw this many times. We need it. We need it again. We need it. Let's replace cosine by 1 minus sine. So this is 1 minus 2 sine squared x. Let's solve for sine squared. That means sine squared is equal to, if I move this to that side, move cosine to the other side, I get 1 minus cosine of 2x, and there's a factor of 2 that I need to divide by. All right, so again, this is just algebra. I want you to go over this, get this back into your brains if it hasn't been in there for a couple of weeks. So if that's what sine squared is, there's no problem sticking in this identity in place of sine squared. 1 minus cosine of 2x over 2. Let's break that up as a half minus cosine of 2x over 2 dx. Okay, does that make sense? Now we don't need a u substitution at all. What's the antiderivative of a half? Yep, x over 2, 1/2 x. What's an antiderivative of cosine of 2x? Or negative, there's a negative cosine. What's an antiderivative of that? I mean, there's a factor of negative a half, depending on how you want to do it. Yeah, it would be sine of 2x, but sine of 2x would have a chain rule that would bring a 2 down. So let's kill off that 2. Do we need a plus c for both of them? No, we just need a 1 plus c. Okay, what should we do? Check. Let's check. Let's check if this really works. If I differentiate x over 2 minus, what is this, a quarter sine of 2x? what do I get? The derivative of x over 2 is a half. This is a quarter. Derivative of sine is cosine of 2x. Chain rule times a factor of 2. That is 1 minus cosine of 2x over 2. You taking a picture? I'm going to post it. The whole thing, the whole PDF goes online. All right. It's up to you. Okay, does that make sense? How did I figure this out? So this is our bag of calculus tricks. Our bag of integral tricks is going to contain things like double angle formulas. Yeah. What else? You'll get lots of practice. Again, the way that you actually learn the subject is by practicing these things. All right, let's talk about what to do with those were indefinite integrals with u-substitutions. How do we do definite integrals with u-substitutions? So definite integrals with u-substitutions. Okay, we're just going to get a lot of practice. Here's an example. Let's integrate 3x squared square root of x cubed plus 1 dx from minus 1 to 1. I don't know what this function is. It's something from minus 1 to 1. What's the area under this curve? Okay. You got a u sub in mind? Yeah, x cubed plus 1. What's du? 3x squared dx. That's good because I have 3x squared dx. Well, what does that mean? That means that the antiderivative of 3x, putting the bounds, the antiderivative can be written as 2 to the 1/2, and then the 3x squared dx together make a du, right? Which means if I put things back in terms of x's, sorry, first I have to actually do the integral. That's u to the 3/2 divided by 3/2 times 2/3 plus c, but actually at this point I don't care about the plus c. Fine, let's put the plus c since it's an indefinite integral. But we're going to stick it into a definite integral once we figure out the antiderivative. So we will have actual bounds. And then I get what? 2/3 times x cubed plus 1 to the 3/2 plus c. So that means I can take this function, this definite, was that? Now we don't need the plus c. We may as well not put the plus c because we're just going to evaluate this. Once we know n antiderivative, we don't need the plus c. So the antiderivative that we know is 3/2 x cubed plus 1 to the 3/2. What did I say? 3/2, 2/3, evaluated from minus 1 to 1. Does that make sense? How we got that? Now we're using the fundamental theorem to know how to evaluate this. We know an antiderivative. This is an antiderivative. We can set c equal to 0. That's a perfectly good antiderivative. And then we'll evaluate it at x equals 0 and x equals 1, subtract off the two endpoints. So what is that? When x equals 1, I get 2/3. When x is 1, I get 2 to the 3/2, whatever that is. Okay, whatever. Minus 2/3 times when x is -1, -1 cubed. -1 cubed is -1 plus 1 is 0 times 0. All right, so the answer is the area under this curve, whatever it is 2/3 times 2 to the 3/2. And if you want to combine the powers of 2, you can, but whatever. All right, that's the answer. There's another way to do this. You can do this. There's nothing wrong with this. We use u-substitutions to figure out an antiderivative. Then we plug the antiderivative back in x values. There's one more way to do this. There's many ways to do this, but there's one more that I want to show you right now. Alternatively, we can say we made this u-substitution. It's an integral of u to the 1/2 du. Can I say that this is from minus 1 to 1? This would be correct in the x's, but it's not correct in the u's. The u's have a different range. Okay, I need to figure out what happens to u when x is -1. So this is not correct. It is not correct to keep the same bounds. What I have to do is figure out what the correct bounds would be. In other words, when, let's do a little calculation over here. When x is -1, what is u? If I put in -1 for x, -1 cubed plus 1 is 0. And when x is 1, u is equal to 2. So it's not these bounds, it's from 0 up to 2. Now I can evaluate, now I can forget that the original integral had to do with x's. I have a new integral. It's the same integral, the integral from 0 to 2 of u to the 1/2 du. Does that make sense? I know how to integrate u to the 1/2. That's u to the 3/2 times 2/3. And I'll evaluate that from 0 to 2. When u is equal to 2, I get 2/3 times 2 to the 3/2. When u is equal to 0, I get 0. So I get the same answer. I get the same answer 2 different ways. I mean, okay, let's keep the -0, but does that make sense? So if you're going to do a u substitution in a definite integral, either go back to the x's and use the original bounds, or it might be easier, in fact, to change the bounds to the u bounds, to the u range instead of the x range. Okay, let's do a couple more examples. Okay, here's an example. Integral from -pi/4 to pi/4 of tan x dx. We already know an antiderivative for tan. Log absolute value of secant. But let's forget that. Let's rederive it if we like. This is an integral from -pi/4 to pi/4 of sine x over cos x dx. The u substitution was the denominator. Cos du is negative sine x dx. I'm just repeating what we did already. And so this will be an sine x dx is negative du. Cosine of x is u, and it's in the denominator. What's the new range of integration? -pi/4. So what's the cosine function? Cosine function looks like this. At -pi/4, this is pi/2. At -pi/4, what's the cosine function? Yes, this new lower bound is √2/2. Cosine is √2/2. What about when x is pi/4? √2/2. They're the same? Yeah, they're the same. There's no area. It's some function integrated from one endpoint to itself. There's no area. This just comes out to 0. Does that make any sense? Wait a second. What is tan? Tan looks like this, right? This was cosine. This is tan. -pi/2, and at pi/2 totes, then it looks like this kind of thing. So from -4 to pi/4, I have something like this. Uh-oh. Yeah, okay, we're still there. Right? Negative part exactly cancels the positive part, and of course it's equal to 0, which we found through this u substitution. In fact, that's a general fact. So here's a, I don't know, theorem or obvious lemma. If f is odd, is that it's odd. Remember, it has the symmetry, 180-degree rotational symmetry. If f is odd, then what can we say about any integral that's symmetric about the y-axis? An integral from -a to a, yeah, whatever time it spends above the x-axis, it'll spend. So any odd function, whatever it looks like, does the same thing until it gets to 0 as it does after 0, except with the opposite sign. So this is exactly going to cancel out. What if f is even? Exactly. If f is even, the integral from minus a to a, f of x dx, f of u du, whatever, if the function's even, whatever it's doing here, it's also doing there. We can double the integral from 0 to a, f of theta d theta. I'm just using different dummy variables so you get used to, so you're not sort of locked in on x being the variable that you have to integrate. Okay, this integral will be the same on the back end as the front end for an even function. All right, let's cover one more topic, which is area between curves. So we talked about area. What we've been doing is integrals, which are area of a function and the y-axis, right? But between curves, so here's an example. Area between curves. Area, find area bounded by y equals 2 e to the x plus x, y equals e to the x over 2, x equals 0, and x equals 1. Oh boy, what in the world is this? All right, so x equals 0 is this line, x equals 1 is this line. E to the x over 2, when x equals 0, this is equal to e to the x is 1 over 2 is a half. So here's a half. When x is equal to 1, I get an e over 2. How big is e over 2? E is about 2 point whatever. So this is just a little bit bigger than 1, right about there. So here's this bottom function. How about the top function? If x is equal to 0, I get e to the minus 0. That's 1 times 2 plus 0. That's 2. Sorry, I'm doing that calculation a little bit quickly. How about when x is equal to 1, 2 over e plus 1 is going to be a little less than 2. So it's like this. Okay, this is the top function. This is the bottom function, and I want to know this area. But what does that mean? We can integrate everything from here to the x-axis and subtract off everything from here to the x-axis, and that'll give us exactly the area in between these things. Right? So the area, very simply, is the integral from 0 to 1 of the top function to e to the minus x plus x minus the bottom function. Minus the bottom function, e to the x over 2 dx. Does everybody see that? We don't have to finish the rest of the calculation. Can we also do it geometrically? Tell. So you're saying if we chop this up into little pieces?
Yeah, no, I'm saying it's like
Yeah, it's a weird curve. It's not something that we can easily, like, it's not just like a triangle where we can look at it and use what we know from geometry. It's some weird function, but the point is that the area between curves is simply the top curve minus the bottom curve. That's the only point I wanted to make. Now here's, yeah, Jen. Yes, you have to figure out which one's the top and which one's the bottom. Yes. If they cross over, okay, so if they cross, we're going to do another example very shortly. If they happen to cross and you want to know the area between the curves, so then you have to figure out where they cross and switch which one's on top and which one's on bottom. Okay, in general, so the area between f and g from a to b, from a to b, in general is the integral from a to b of f of x minus g of x, absolute value dx, because the absolute value is the positive difference, right? That's the distance between them, which whoever is on top, the absolute value will give you something positive. So you do have to be able to figure that out. Let me show you one other thing that will be useful. So here's one more example. Find the area between square root of x, y equals 0, and y equals x minus 2. Okay, I know what y equals 0 is. That's just the x-axis. That's good. Y equals 0 is the x-axis. Square root of x, I also know that's this kind of thing, square root of x. Y equals x minus 2 is a line. It starts at -2. It goes up to, when x is equal to 2, I get 0. When x is equal to 4, I get 2, which means it hits this. So this is this line. So the area bounded by these three functions is this. You see that? So there are two things you could do. You could chop it into two pieces and compute this area, which has one lower bound and upper bound, plus this area, which has a different lower bound, same upper bound. Okay, you see how you can do that? Or, so two ideas. Idea one is it's the integral from 0 to 2 of root x is the top function, 0 is the bottom function, plus the integral from 2 to 4, root x is the top function, 4. The bottom function is x minus 2. You see that? So you have to break it up. Or idea two is, can't we integrate with respect to y? Can't we chop things like this? Won't that make our lives easier to chop things like this? What would that mean? What's the equation of this line in terms of x? X is equal to, if y is equal to x minus 2, then x is equal to y plus 2. And how about this curve? If y is root x, then x is y squared. Who's bigger? Who has larger y values? Y plus 2 is farther from the y-axis. So this is also the integral as y goes from, bless you. It's an integral dy. We're going to chop into little pieces of y, dy, little dy rectangles. So dy. Y will range from 0 up to, where do they intersect? 4, 2. Y will range from 0 to 2. What's the upper bound? Y plus 2. What's the lower bound? Y squared. Let's evaluate both of these sides and see if we get the same answer. You see how we did that? Does that make sense? So instead of breaking it up into two integrals, which is a little bit annoying, it's not that annoying, but it's, two things you have to compute. You can compute it in one fell swoop by chopping it in the y direction instead of in the x direction. In the y direction, it works exactly the same as in the x direction, just we're not maybe as used to it. But there's nothing wrong with this chopping. Let's do this one first because it's easiest. The antiderivative of this thing is y squared over 2 plus 2y minus y cubed over 3, all evaluated from 0 to 2. When y is equal to 2, I get a 4 over 2 plus 2 times 2 plus minus 2 cubed is 8 over 3 minus, what's the value when y is equal to 0? 0. Okay, so this is whatever it is. Can we figure out what this is? 4 plus 2 more is 6. 6/3 is 20 minus 8. What is it? 16/3? Did I get that right? 16/3? 24. Yeah, I think that's right. So while we evaluate the other idea, did I get it wrong? 10/3? 18/3 minus minus 8 is 10/3. Thank you. That's better. Does that make sense? This is a little bit more than 3. This is 6 minus almost 3. Yep, makes sense. Okay, how about the other integral? The other integral 0 to 2 of just root x. What's the antiderivative of root x? X to the 3/2 times 2/3. And that's being evaluated from 0 to 2. Okay. Plus, what's this thing? The antiderivative is 2/3 x to the 3/2 minus minus x means minus x squared over 2. Minus -2 means plus 2. The antiderivative of plus 2 is just plus 2x plus 2x. This whole thing is evaluated as x goes from 2 to 4. Okay, so check this out. I'm going to get a 2/3 2 to the 3/2. At 0, I get nothing. How about here? I get 2/3 times 2 to the 3/2. I'm sorry, 4 to the 3/2 times 4 to, I'm evaluating this at x equals 4. 4 to the 3/2 minus 4 squared over 2 plus 2 times 4. That's the value at x equals minus the value at x equals 2. At x equals 2 is 2/3 times 2 to the 3/2 minus 2 squared over 2 plus 2 times 2. I'm sorry, I'm doing the algebra quickly, but hopefully you're following along. We're almost out of here. Here's the beauty. This complicated, we didn't have any square root of 2's in our answer before. It was just 10/3, right? It's just 10/3, no square root of 2's. This has a square root of 2, but so does this. So this and this cancel out. And hopefully when the dust settles, what's this? What's the 4 to the 3/2 is 8. So this is 8 times, yeah. So this is all gonna work out. 4 over 2. 2, so this whole thing is a -2. This whole thing is contributing a -2. This is 16 over 2. This is a -8. -8 plus 8. Oh, good. The -8 and the plus 8 cancel. I have a 16/3 minus 6 is 10/3. Okay. Again, I'm sure I did that algebra and arithmetic too quickly, but we do get the same answer. Why did I write 6? I don't know. It's 10/3. I'm too tired. All right.